Well, good morning. How was the weekend? Stressful? Just work, right? There's no when you're in school, there's no such thing as a weekend, right? Your weekend happens between semesters sometimes. Yeah. Um, I'm not one to sleep very long. I've got back problems and things. Usually means I can only do about 6-7 hours at a time. I slept for like 13 hours on Saturday. And then Sunday was like another 15. And yet, like, I can't, this post COVID thing, like, I just can't seem to get my energy back. So forgive me if I sit down a lot during lecture today. No more prednisone, so I won't be quite as wired, but I am on performance enhancing drugs, namely my inhaler. So we'll see how that goes. All right. Good news. Looks like just about everybody was able to get like chapter 1 homework. You at least cheated well enough to get 100% on it or whatever, right? The few people that were having trouble, I was managed to chase down, figure out what was going on, and we'll get them taken care of. So excellent start there. I know that's so quick, right? You're in school, first Saturday, homework's due, but we're jumping in, and we're going to do some physics today. But before we get to that, we are going to do the aforementioned and threatened quiz. What quiz was that? 2.1 and 2.2. So hopefully you've got your quiz sheets. Let's get into the meat of chapter 2. This is not a secret, but it seems like one. What you are here to learn isn't really physics. Physics is an excuse. Physics is nice. You're going to need it to be able to do all the things you're going to do in your careers. And you'll refer back to it and may or may not remember this class, but you'll get there. What you're here to learn right now is problem solving. The purpose of college, especially the first couple of years, is to learn how to learn. When I talk to engineering firms and people that hire you guys out of school, I ask, like, what can we do? What can I do as a teacher to get you the best new employees possible? And I never hear things like, well, I need the world's best engineer. I always hear things like, can you please teach them how to use a telephone? Like to talk to people. That's more and more now. But mostly what I hear is we need people that know how to learn. We're going to teach them how to be good engineers. What we need them to be able to do is learn and learn quickly. So I think the secret of physics success, STEM success, and to a larger degree college success isn't necessarily the content. You'll be asked about content, you'll be quizzed on it, you'll be tested on it. But if you learn how to learn, and in this class particularly how to problem solve, you're going to discover that every single homework problem, every single exam problem, they're all the same problem. The details are different, but they're the same problem over and over again. And we approach them all the same way. A lot of books do this on the surface what looks like very differently. Some books hardly mention it at all. I've seen books that like have a 17 to 21 step process, right? Okay. I am a simple person. I have a simple brain. I have trouble remembering more than 3 things at a time. If my wife is giving me a list of stuff to pick up the store and she goes past 2, it better be texted to me or it's not going to happen, right? So what I've done is I've boiled down the physics problem solving method, okay, to 4 steps, which is really pushing my intellect quite a bit, okay, with 4. Usually I can remember 3. So I'm going to introduce to you Mr. Balogh's summary of a problem-solving method. You've probably heard this as the scientific method. Scientific method is not what you think it is, or a way of going at stuff. But what's not going to be here is things like hypothesis and all that kind of baloney, right? Because science, if it's anything, is a systematic approach to figuring out how things work, right? And we need to overcome that initial desire when we see a problem to panic, to run home, jump in bed, pull the covers over our eyes, assume the fetal position, and hope that the world goes away. Because that's real. That's going to happen. You don't like word problems. I know it, right? But the universe is a word problem, okay? And we need to instill in you a confidence, right? That you can take a look at something that you like, I have no idea where to start, and give you a place to start. Give you something to dig into, right? And so this is what this is going to look like. And you're going to see me do this over and over and over again. You're going to get sick of this semester, because this really is what you are here to learn. So I like to kind of break this down there's really only one math step in this entire process. You want to guess which one it is? Where you're actually doing math? It's the do it step. Notice that it is step number 3, right? So if you are starting off your problem solving, if you've got a problem and you are just sort of trying to throw equations at the wall to see what sticks, you're doing it wrong. Because you don't start with math. You start with a strategy. You start with a goal in mind, identifying what it is you're being asked to find, even if you don't understand the question. Like, what is it asking? Is it asking for time? Is it asking for position? Is it asking for velocity? Is it asking for Excel? Like what? Reading comprehension, right? Okay. And again, visualization, this ability to bring information together. It doesn't necessarily mean having a brilliant ability to conceptualize 3D space and all that kind of stuff. This is a catch-all term that could mean, well, what do you know? What do you don't know? Where are you trying to get to? Where are you starting? Like, you're laying out the information that you have. In physics, we call this finding the boundary conditions. We need to know sort of the limits of the map, as it were, right? What information do we have and where are we trying to push beyond it? And so the visualization step is a conceptual step. It's a pulling together of ideas and trying to see, okay, is this Newton's laws? Is this kinematics, right? Taking a big picture, starting big before we narrow it down. One of the things that novices in any skill try to do is they start way too focused. They focus usually on the wrong things. And an example I like to use of this is teaching people how to climb mountains. I'm a former climber and I would teach people how to climb. And you take them to the gym or you take them to Yosemite or something, and a beginning climber will sit there because their life is on the line. They think their life is on the line, right? Okay. And they're going to watch really carefully what everybody is doing, right? And so they'll watch, say, me or somebody else climb something. And they're watching. And when you ask them to do it, what do you think they try to do? Exactly what we did, right? Mimic what's going on, right? Because you don't know what's going on. But that is a road to failure. That is a road to falling. Because there's no understanding of why it's important that the climber put their hand like that or shifted their weight onto a different foot. And so if you can take a step back and not just mimic, right, but try to understand why did Mr. Balogh choose that equation? Why did that climber move that way? Now what you are setting up is the ability to climb anything and to do any problem. If you're just trying to memorize all the homework problems in the hope that you're going to be able to do it on the exam, you're thinking like a novice, right? And we need you to think, notice, I'm not expecting you to be an expert. I want you to think as an expert would, right? Think of the big picture, think of why, get some framework. And your brain and in your desire to shortcut this and make this happen as fast as possible because physics is painful, your brain's going to want to not do any of this. So you have to condition yourself. You have to convince yourself, okay, I can sit down, I can do this, and it's important. Okay, and then we strategize, we come up with a plan. Once we know kind of where we are, where we want to go, what we have, what we don't know, then we can try to put together some sort of plan. And that plan often is dictated by physics. The physics happens in the first two steps. Once we have that plan, we execute it, we do it, which is usually some mathematical operation that's going to get us to the thing that we want to find. And then the very important part of going back to make sure our answer makes sense, right? In the context of what we've given, right? Can we be certain that this is right? So what I want to do for the rest of the day today is model this for you. And I'll model it a lot. I will never expect you on an exam, on your labs, whatever, to do my method, okay? I know it works for me. It's worked for a lot of people. It's a fairly generic method. If you come up with a different way of organizing your thoughts and your information, fantastic. I read all kinds of physics all the time. That's my expertise, right? And if I don't understand what you're doing, I'll come and ask you. I'll come find you, right? So please don't feel like you must replicate what I'm doing. You'll never be graded on this method, but I will expect you to be able to communicate what you're doing clearly. Why did you pick that equation? What are you thinking? What are you doing? All that sort of stuff. And so come up with a method that lets you do that. Okay? All right. We are going to do this in the context of chapter 2, which is kinematics and in one dimension. And we'll do it horizontally and then we'll do it vertically. Kinematics is how things move. So we're going to talk about cars. We're going to talk about baseball. We're going to talk basically anything that's moving that has velocity, position, acceleration, time. We're going to try and figure it out. Now, I am going to give you a toolbox. And I'm going to write this on the abomination that's up here. And as soon as I do, your brains are going to want to shut off. Because it's math, right? Don't let it happen. Remember, math is a language. It's a compression language. It takes really big ideas and gets them really, really tiny on the page, okay? And you'll see a lot of equations in your book. I think there's only 3 that you need from chapter 2. I think they list a total of 6 in some sort of golden box or whatever, right? Okay. They're all, these are the only ones you need, okay? Can you guys see this? Is it bold enough, or is there too much glare or anything over there? We're good? Okay. Jeez. I wonder, is blue better or black? I don't remember what you guys told me. Black? We're still learning how to do stuff in this room. It'll only take the rest of my career to figure it out. Well, look, I got an eraser. No place to put it. All right. Until my black pen wears out. Jeez. Can we go home? Can I go back to sleep? All right, let's see here. What have I got? Lecture will continue after these brief interruptions. All right. Ooh, this one even squeaks. Okay. What does that say? How are these different? What's the naught, the sub-zero on this mean? It means an initial. So the velocity it starts with, right? So if there's no naught on it, that's final. So whatever speed it ends up with comes about because of the speed that it starts with, plus its change in velocity and time. So a big, long idea, right, about the relationship between velocities and accelerations and time, all compressed into a tiny, tiny statement. Just like the videos you watch are compressed and decompressed as they're sent to you over the internet. They start big, they compress down, they get to your device, and then they come back out and they either get blocky or not, right? Mathematics is a compression algorithm. It takes ideas and puts them into small spaces so that we can then read them back, right? Okay, so then we have a delta x equals v naught t, v, here we go, t, plus 1/2 at squared. I'm writing them on the abomination because I got to refer to them a lot. All right, so what's the delta x? Displacement, right? A change in position. Not just a change in x. It can be any, it just doesn't have to be horizontal. It could be vertical. We could do change in y, right? But the idea here is that there's some change in position of where the object is located, right? And that change in position will come about because of how fast it's initially going and how long it travels that way. That kind of makes sense, right? And if you look here, if we ignore this term right here, distance equals velocity times time. Yeah, duh. 1/2 is just, okay. And then changing velocity and time squared, right? And then the third one, v squared equals v naught squared plus 2a delta x. That right there, in my opinion, is the entirety of the toolbox that you need for chapter 2. In chapter 2, you'll see a lot more equations. They are just variations on a theme of those three. You'll see a fourth equation. It's useful, but like I said, I have trouble remembering more than 3 things at a time, and so I refuse to learn it. And the fourth equation you can get from these 3 anyway. The tools don't tell you how to solve things. They are tools. If you're building a house, you don't go to the hammer and say, how do I build a house? Right? The hammer is there to help you build the house, but in order to build the house, what do you need? You need a plan, right? Otherwise the house is going to look really funky, okay? You need some training expertise on how to do it, and you need tools and materials and people to help you, right? Okay? The toolbox, these right here, those are tools. You don't reach for them first. You don't go find a screwdriver and then say, you know what, am I hanging a painting or am I fixing the potted plant, right? Like you don't do it in that order. So don't do it in that order. If you come to me, Mr. Balogh, tell me which equation to use. What you're telling, you just asked me a question. You just said, Mr. Balogh, help me skip physics. So I can just solve. Do you ever imagine you'd be in a class where you were begging to just do math? Welcome to Physics 4A, okay? So these are tools. We're not going to start here. We're going to refer to them, and they're going to help us figure stuff out, right? But don't let them be the end all. They're just a part. They're just a part. All right. So here is an example. Again, I will have this for you on the PDF. You don't need to worry about copying it down unless you want to. What I would like you to do right now is see if you can determine just by yourself, where are we going? What is it asking us to find? Just do part A. Don't worry about part B yet. Is there a word that's jumping out at you about what you're supposed to find? Acceleration. What is the acceleration? They're asking us to find acceleration. So we already know where we want to go, but the hard part might be where are we starting, right? Okay. What do we know? What do we don't know? I'm seeing numbers. I'm feeling scared. I want to go home. What do I know? Time? Well, they gave me 3.1 s. Yeah, seconds, right? And then they gave me a meter per second, which I know is a unit of velocity. So that's got to be initial, final? Okay, yeah. Okay, wait a second. Is there a way for me to keep stuff organized? Is there a list of things that I could know and not know. Where's that list? Told you not to start here, but we're going to start here. There's a list right here in the toolbox. This toolbox is for one-dimensional kinematics with constant acceleration. It comes with a little bit of, some limiting factors, right? So as long as our acceleration is the same throughout, which it will be for chapter 2, so you don't have to worry about it, okay? Then these apply. If you slam the brakes on in your car, is your acceleration constant? Are you slowing down at the same rate all the time? No, okay? Your brakes work better the slower your car goes, okay? And so more and more change in velocity tends to happen towards the end of the braking period if you've slammed on the brakes, right? A lot of people hit the brakes kind of hard and then come off of them to try and keep the acceleration the same throughout. But we're talking about slamming on the brakes. So you're going to say, Mr. Balogh, well, that's physics land. That doesn't exist. That's not real. That's fair. But guess what happened if I started with real? How many of you would be able to do the second chapter homework? I'm not sure I would anymore. Real is hard. So we'll make believe. We'll just pretend that the acceleration is constant for now. Okay, so is there a list of things I could know and not know? Can I know and not know my final speed? What's this? Initial speed. So, okay, we're getting to more than 3 things. I better make a list. Okay, so what I like to do, especially when it's like chapter 2 kinds of things and I'm doing kinematics, is I do like to make a list. Whoa. V naught, A, T. Again, where did I get those? They came right out of my toolbox. I know my tools need these things. I'm going to make a list. Okay, what comes next in my toolbox? Delta X. And then V naught. Is V naught already on my list? Yeah, what about T? Yeah, already on my list. A? Yeah, T? All right, are there any new things? No. What I've got on the screen is the total list of things I can know and not know, the limitations and power of this toolbox. So now I can go through the problem and see if I'm given any of this stuff, right? Do I know what the final speed is? What is it? This doesn't say 0 up there. Comes to a complete stop. Okay, so here comes reading comprehension, right? Oftentimes you have to read between the lines, right? It may not say 0, but if it says it comes to a stop, that means 0, doesn't it? Okay, so we're going to assume that the final speed, 0 meters per second. Do we know how fast it's going? Right at the instant it starts to slow down. 27 meters per second. Do we know the acceleration? They don't give us any of that. Do we know how long it took? 3.1 seconds. And do we know how far it went? No. Okay. So, and why am I putting question marks? Why am I not just leaving it blank? Close. Future you is going to come back to this. Is going to wonder, what the heck happened? What did I do? Right? For me, a question mark means that I thought about it. Right? I asked the question. What is the acceleration? Not given. I don't know. Question mark. So that future, when I come back to this, and I'm looking at it going, did you ever think about the acceleration? The question mark saying, well, yeah, at some point I did. I might have gotten it wrong, but at least I try. If I just leave it blank, I don't know, right? Like it's a mystery as to whether or not I was conscious that day or something, okay? Okay, so notice, how many pictures have I drawn so far? None, right? Like I'm not a scientist. I'm not an artist. I went into science for a reason, right? Okay. Scientists' art is like drawing a graph. So sometimes, but maybe a picture works for you. I'll do one later where I'll draw a picture, okay? So please don't be hemmed in by doing exactly what I'm doing, okay? But if this idea of a list is helping you, right, with that thought and idea of organizing the information you have, do it. If drawing a picture instead is better and you just draw numbers that are attached to a picture of a car or something, by all means, do that. If being able to close your eyes and go, okay, I'm driving along, I hit the brakes, and I come to a stop, put you into the mindset, right, of the context of the problem, by all means do it. That can all be a part of visualization. For me, it's getting the information down in a way that I can see what I know and what I don't know. Okay, so I've kind of gathered information, I've organized sort of my thoughts, but now I need to figure out how I'm going to figure out what they want. So what are they asking me to find? Acceleration. And I'm going to come in and I'm going to circle the thing that I am being asked to look for. So acceleration is the thing I'm being asked to find. And again, for me, it's me, that circle is going to communicate that this is the thing you're looking for. Further on down the process, when you are totally lost, when you are in the algebra jungle and the snakes are coming after you, a reminder, right, of what we're looking for could be really useful. Okay, now I have to figure out how I'm going to get there. What do I know? Initial and final velocities and time. What do I want? Acceleration. Is there a tool that can help me put these things together so that I can be successful? Notice, we've done a lot of work before I've even asked, like mathematically, what the heck is going on up here, right? Symbolically, I pulled out the list, but mathematically, now I'm going to turn to the tool, right? So what of these three equations do you think might be the best one for figuring out the acceleration, knowing v, v naught, and t? Kind of a dead giveaway, isn't it? Because what's the other thing we don't know? Delta x. So do we want delta x in a tool? We have no idea what it is, right? So stay away, okay? So the fact that the second and the third one both have delta x in them makes them a little bit radioactive. Not terrible. Bananas are radioactive. But the first one seems to have what I need, okay? But it's not sort of all the way there yet, right? It's got what I know, it's got what I don't know. It's only got one thing that I don't know in it, which is a plus, but it's going to need a little bit of massaging, isn't it? Okay? Because I need to solve this array. So what's the plan? What's the strategy? Too detailed. Use the first equation and solve it for A. Everything you said was right. What you guys were saying was correct. But future you, when you come back to this, how golden would it be to have a real simple statement about what you were attempting to do? When you go back to study, when you go back to figure this out, right? Having just that simple, use the first one, solve for A, gives you, again, a mental target, and then you can start doing your math, okay? So, once again, I will not grade you down if you don't do this, but I would strongly recommend, especially like on your homework, because you're beginners and you're doing this for the first time, you're going to need to come back and study this, write down your plan. I'm normally not going to do this because I'm going fast in lecture and I want to show you other things and there's specific things I'm trying to target. But in this case, I will write it down and you get to see just how bad my handwriting is. Okay? So what's the plan? It is use first equation and solve for A. Right? Just a simple statement about what it is you're going to attempt to do. Now that we have visualized and strategized, what do? We do it. We got it down. We got to see if we're going to get anywhere in this, right? So first equation, copy it down correctly. Big problem Mr. Balogh has. All right. I need to solve this for A, right? I've already mentioned this, but I'm going to mention it again. You're going to be supremely annoyed that I will do as many things symbolically as I possibly can before putting numbers in. Numbers are evil, and they're always out to get me. And it's easier to figure out where things went wrong in symbols than it is if a numbers combine and then you don't know where that sort of number, what it means or any of that kind of stuff. Again, I will not grade you down if you don't do it my way. If you want to do everything in numbers, fine, do everything in numbers, right? But it's very difficult for me to give you partial credit or benefit of the doubt if I can't see or follow, right, what's happening. It gets lost in numbers. But in symbols, they maintain their relationships. So, and I do math fast in here. You're going to be like, where's the beta stop? Oh, show me how to do the math. This is not a math class. Physics class, right? I expect you to already know how to do math. So the first thing I'm going to do is I'm going to subtract V naught from both sides. I see it as moving it to the other side of the equal sign, and when you do that, you change its sign. Okay? And then I'm going to divide both sides by A. Nope. Try again. T. I love electrons, the fact that I can just do that. Okay? Right? So that leaves me with what? A is equal to V minus V naught over T. And then now that I've kind of gotten to where I want to be, I can go ahead and put my numbers in. Last step. What's the final speed? Okay, and the initial? 27 meters per second, and then over 3.1 seconds. Now, unit-wise, what happens to the units here? The seconds don't cross out. It's a meter over seconds times a 1 over a second. So it's a meter per second squared. What the heck is a meter per second squared? It's units of acceleration, right? Woohoo! We got that part right. Okay. Would you say this was -8?
No, just 8.71.
8.7? We'll just do 8.7. Okay. All right. And one of the things I will ask you to do, again, if you don't do this, I'm not going to knock points off. But this really, really helps, especially in grading exams. When you get to an answer, box it. It just, in math, they do like QED or do something, right? But like in physics, generally, when we're working on paper, like not published journal articles, but like everywhere else, we tend to just box where we, our answer, our result, okay? As a way to say, look, this is the thing, right? So I'll remind you to do that. But again, if you don't do it, I'm not going to take points off. It's just I got to hunt longer to find your answer, and the longer I hunt, the angrier I get. And you don't want that. Okay, so all right. So we've got an answer. Yay! What do we do now? Go home. No. What's the fourth step? I heard it. Check it. Oh, well, in Wiley Plus, this is easy, right? I go in, I type number in, green box of joy, red box of doom. I understand that we're training you poorly when it comes to these online homework systems. We're training you with the idea that the internet knows all the answers, and you can just refer to Wiley Plus. On the exam, in your jobs, in the universe, is there a green box of joy? No. Just more questions, usually, is usually what it is, okay? Having another way an independent way of figuring out what's going on, really useful, right? And so several skills come into play here. I know that most of your check it is going to be put it in Wiley Plus, yay green, move on with life. But do yourself the favor of analyzing. Okay, what was it that I did that I got this right? Or, oh, red box? Okay, remember, Mr. Balogh said I'm supposed to believe that it's wrong and I'm right, so I'm going to go figure out why, right? I'm going to prove it. How would we prove? Is there another way that we could figure out this acceleration? I love that answer, right? The answer of just plug it back in and see if we get like a starting value. I don't know about you. I've tried that throughout my entire career. Garbage in equals garbage out. I've done the same mistakes over and over again, and I can prove mathematically that I'm right, and it's totally wrong. So it's mathematical, but it's not physicsy. So yeah, I taught you a trick already, kind of how to do this. No? Do you remember order of magnitude? No? Mr. Balogh talked about it. I still don't understand what he was talking about. Let me show you. How fast is this car going? About. Round number. 30-ish. Right? And about how long is it taking to slow down? About 3 seconds. So if I'm 30 right here, and I have to divide this into 3 equal periods of time, about how much do I have to reduce my speed every period of time to get to 0? I started with 30, right? And so about 1 second later, I need to be at 20. And then a second later, I need to be at 10. And then I need to be at 0. How much did it change right here? About 10, right? How much did it change right here? About 10. And how much did it change right here? About 10. Is 8.7 about 10? Yeah. There's an order of magnitude calculation, right? If I had gotten 67,000 and then realized, well, I should have only taken 3 seconds, right? Then I'd know there'd be a problem. There's another thing that is screaming at you that is demanding to be checked. The negative sign. Never, ever let a sign go by without you interrogating it. You nail it to the wall and you find out why it's there. And that includes the positive signs that are never written, right? They're sneaky. They're little ninjas. You gotta find them and ask them. Why is that negative sign there? What is it trying to tell us? It's slowing down. Is that what the car is doing? Yes, the car is slowing down. So we expect to get a negative acceleration out of this, and indeed we have. All of these are checking the answer, right? So sometimes you can't do an easy order of magnitude. I'll show you an example here in just a minute where the order of magnitude will fail you, right? In which case, we'll come up with some other methods. Okay, what I want you to do right now is turn to the people next to you and tell them how you would solve part B. I want you to strategize and come up with a simple statement about how you are going to find how far the car traveled during that period. Go. All right, why did I circle delta x? That's what I'm going for this time, right? And do you see how I put negative 8.7 in? Because now it's something that I know. Just trying to recycle my list here. You can make a new list if you want, but I'm being lazy. Okay. What did you come up with? What was your plan? Use the second equation, period. Because the second equation is already solved for x, isn't it? Did anybody come up with an alternative method? Ooh, the third equation? Is the third equation a possibility? Yes, the plan would be use the third equation and solve it for delta x. Both work because we know all the other things and we're just looking for delta x, right? Advantage of the second equation? We don't have to do any algebra, which is less error, right? So let's use the second equation. But it suggests something. What could the third equation then be used for? If you have two ways to do the same thing, what can you use the second one for? To check it. And what percentage sure do you want to be on an exam problem?
110.
Right? So sometimes it's worth it to just do it again real quick to make sure you're getting the right answer. Okay, I didn't write down my simple statement. Use second equation. Boom. Okay, so no algebra required. Initial velocity. I hope that this becomes the hardest part for you. I know it's the hardest part for me. Putting the right number into the equation. What's the initial velocity? 27. What's the time? 3.1. Plus 1/2, and then negative 8.7 and 3.1 squared. What did I leave behind? Yeah, I didn't put units in. Whoa. I'm doing this dangerous. I'm risking flying too close to the sun here. Why have I left the units off? To confuse you? I mean, they confuse me. They definitely confuse me. This is a meter per second, right? And then this is a second. And then over here, I've got a meter per second squared times a second squared, right? And so will the units work? Yes. Let me show you a secret. Not a secret. A feature. The toolbox equations are dimensionally consistent. Mr. Balogh, you just use big words. I know I use big words. It makes me sound smart. What is this? It's a velocity. So what's this? It has to be a velocity. See the equal sign? A velocity has to be a velocity plus a velocity. You cannot get an apple by adding apple plus orange. What does everything have to be? Every term has to be what? Velocity. What does every term in this equation have to be? It has to be a position. It has to be a displacement, right? It has to have units of meters. That's dimensional consistency. Okay? It's built in. And if you use the standard metric units for everything that goes into these equations, for example, time. If you're given time in minutes, don't ever put minutes in here. What should you put in? Seconds, right? If you're given a speed in kilometers per hour, what must you put it into? Meters per second. If you go to the standard SI unit for these things, you are guaranteed to get the correct unit out. It's stamped in, it's hard-coded into the algorithm. So, choose, right? Convert everything into the standard unit right off the bat, which is what I do, and then I don't have to worry about my units there ever after. I know that if I'm solving for position, it's going to be in meters. I know if I'm solving for acceleration, it's going to be in meters per second squared. The answer might want it in kilometers per hours cubed or whatever, right? And I can convert it later. But I know that my calculations will work and I don't have to have the mess of all the units traveling along. This is a bad Mr. Balogh thing to do, because really what I should be doing is modeling the correct thing, which is having the units everywhere in all your calculations. But visually, I get confused. I'm confused enough with numbers. But to put all the units on there, bleh, okay? And I like to use the power of things that have been solved for me already, and the units problem has been solved. What's the price you pay? What must you do for this to work? All your units must be in the standard metric units, right? So if you're willing to pay that price, then you can get rid of a lot of cognitive load in carrying units through your calculations. Have I talked long enough for anybody to figure out what this number is? I got 41.9. So 42. Give it a box. All right, how do we check it? We already said. What's one way we could check it? Use the third equation, right? We have another tool that we could pseudo-independently check to see if we get the same answer, right? And if we did the algebra, boom, get the same answer. We're good. You will. I already did it, so that's okay. Another way to check is to do a order of magnitude thing again. Only this time it's going to kind of fail you. And what you have to do, instead of an order of magnitude calculation, what you have to do is you have to fall back on sort of your knowledge, your experience. 42 meters. How far is that? Is there anything in your everyday experience that you could, like, what's a meter? I didn't bring my meter stick. What's a meter, approximately? It's about a yard, right? Okay? A yard is a little bit shorter than a meter, but that's okay. So it's about a yard. And we kind of, if you grew up in the United States, kind of know what yards are. And American football? What's the size of an American football field? 100 yards, right? So we're talking here, order of magnitude, about 50 yards, right? Ish. So is it reasonable that a car should be able to stop, like going 60 miles an hour, would you expect it to be able to stop in about half of a football field's worth of distance? Yeah, I mean, that seems reasonable to me. If we got an answer that was like, well, it's better stop in the end zone, then we know there's a problem, right? Cars don't go from 0 to 60 in, right, the width of this room. Or if we'd gotten something like, well, you got to go 5,000 yards, right? Okay, something's wrong. Okay, so sometimes we can fall back on observation, right? We've observed something to happen. Now we're trying to model it, or we know something about it. This isn't always going to work for you because we're going to be in parts of physics where your intuition is going to lead you astray, which is why it's nice to have another way, like another tool, right, to be able to go and do that check for you. And again, I know you'll just use Wiley Plus, check your answers, which is fine. It's the tool we've given you. But I'm trying to teach you a higher, better way, independent of that. Because there's, again, no Wiley Plus on the exam, right?
So in order to check your answer with that third equation, you have to basically solve for x.
Yeah, use the third equation, solve it for delta x. Yep. And if you get the same number, you'll probably get like 41.8. There might be some round off error, but you got it. Okay. All right. So now, could that problem have been done faster? Easier. Some of you are probably sitting there going, Mr. Bailiff, yes, I get it. I know. This was an easy problem that was done using that method to show you the method. So here is another situation that ratchets up the difficulty. And if you're just throwing stuff at the wall, this one can be very difficult to do. But what I want you to do for the next 3 or 4 minutes is together, not just by yourself, but just immediately turn to each other and start visualizing. Make your list. Draw a picture. Start talking about what it is you're looking for, right? What it is you know, what it is you don't know. And spoiler, I expect you to get stuck. Go. So are we getting stuck? Are we running into any difficulties yet? Is there something different here? How many of you drew a picture? I'm just curious. Yeah, some of us drew a picture. Okay, I'll draw a picture. Let's see. Cars look like this, right? And they started 10 meters apart from each other. I'm going to call car number 1 the one in front. We'll call car number 2 the one in back. And then they travel some distance and they go boom. Okay. So there's a picture, right? This is this could be a side view, or it could be like a drone's eye view. Either way, same difference. Okay. What is the final speed? No. Is there anything here that tells you that it comes to a stop? Oh, Mr. Bailey, you tried to trick me. No, there's nothing in this. So don't make assumptions if you're not told information about it. Do we know how fast the car is going? No. Do we know how fast it is when it starts? Yeah. Plus 27. Why am I putting a plus sign in front? I'll call it moving positive to the right, okay? Do we know the acceleration? Does anybody see a problem? Yeah. Yeah. We have different accelerations, don't we? So what do we do now? 2 lists. Mr. Bailey, you didn't tell me that. How was I supposed to know that? Remember, knowing is how you know stuff. Now you know. So if you have more than one object in a problem, what are you going to do? Going to make 2 lists. If you have 3 objects? If you have 10,000? Yeah. Start doing statistics. All right. So we need, so this is going to be car, what is this? Car number 2? Sure. And then car number 1. And we'll make a new list, V naught, A, T. You can get all formal and do like V1s and A1s and stuff, but I'll try to keep these separate. Okay. So car number 2, the one that's behind, what's its acceleration? It's 0. Oh dear. Mr. Bale just yelled at me for assuming something, and now I don't know. How do we know that the acceleration is 0? What words in the problem are telling us that the acceleration of the behind car is 0? Continues at same speed. If the speed doesn't change, the acceleration is 0. Do we know how long it takes? No. Do we know how far the car travels? No. 10 meters is how far apart they are, but not how far they travel. So, don't know that. That's a lot of question marks, isn't it? I'm starting to get nervous. Okay, car number 1. Okay, do we know how fast car number 1 is going? Final, like after they hit. Some of you want to say 0, right? Because you want to say, well, will they hit and come to a stop? The toolbox can only handle when the acceleration is the same. Once they hit, the acceleration is going to change. That's a different problem. So I'm going to put, I don't know, positive 27. Acceleration for car number 1. It's they tell us, right? From our problem before. I don't know time, and I don't know how far it went. I do know the final velocity of car number 2. If it never changes its speed, what's its final velocity? Same as its initial velocity. Okay, so there's my lists. I'm visualizing. What are we after? What are they asking for? Time, right? Time is what they want. Are the times the same for the cars? Is there a different timeline for car 2 than there is for car 1? Or do they inhabit the same space-time continuum? Yeah, second one. Okay, so time is the same, and often is. There's no like different times for things. Okay, so what about displacement? Do they both go the same distance? They tell us that there's a difference in how far they go. What's the difference in how far they go? 10 meters. So if the first car goes 100 meters before the collision happens, how far has the second car gone? 110, right? It has to go an extra 10. Or if you want to think of it, the first car goes 90 and the second car goes 100, right? There's that difference of 10. But now we're arguing over where 0 is. Whether it's 100 and 110 or 90 and 100, we're simply arguing about where we want to keep track of where 0 is. So where's 0? Is 0 at the first car or is 0 at the second car? Okay, I heard first car first. So if we put 0, and it doesn't matter which one you pick. What matters is once you pick, that you are consistent with your choice. I'll explain what that means here in a second. So if we say 0 is at the first car, that's where 0 is, right? Then what is the initial position of the second car? Be very careful. -10. And why is the position of the second car -10? It's to the left of 0. Do you see it? Now, if we had put 0 at car number 2, right? If we had put 0 over here, then what would the position of car number 1 be? +10. Very important. That's what I mean by be consistent. Make a choice. Doesn't matter which one. You get it right either way. But once you pick, make sure you get the right signs on things based on your choice. Okay? So this delta x down here can be expanded, right? This is an x and an x initial, isn't it? We don't know where the final position is, but we do know the initial position is different. Car number 2 is going to be at -10 meters. Car number 1 will be at 0. And that delta x is sitting there. So what you want to do now, and I'm going to shortcut this because I want to get to the last part of chapter 2. You're going to want to use the second kinematic equation because it is the thing that's going to let you have these two things talk to each other. And you're going to write it down twice, once for each car. And because the final positions are the same, they hit each other in the collision. They're going to be at the same place at the same time, right? You can solve each of those equations, the red one and the blue one, for x final, which is an unknown, and then set them equal to each other, and then all you've got left is t. So when you encounter two objects in an equation that are, or in a problem that are interacting, what's your, now that you know, and knowing is how you know stuff, what's your sort of overall plan going to be? How many lists are you going to make? 2 lists. And then, more than likely, they're going to talk to each other through the second equation. Second equation really wraps together position, velocity, and time all in one package. And so it's used quite often. To expand on this, in general, if you're looking for delta x, do you want to use the first one? No, why not? There's no delta x in it, right? Okay. But they give you clues, right, as to what is useful. If you don't know what time is, which one of these are you going to try to use first? If you don't know time, then the third one doesn't have time in it, right? And it could be used to find something else that you're looking. If you're looking for time, you better use one of the others, right? So the tool is trying to tell you what it's good for. Don't use a screwdriver to hammer a nail in, right? All right. Let's not do this one. We'll get to that later. We need to talk about vertical things, because one of the things your book does is a travesty. When we go vertical, we are going to be allowing objects to have a singular acceleration only, and that is free fall acceleration. We're going to measure it tomorrow in lab, but again, we're not really measuring it, we're just learning how to do lab, right? But all objects, when they are dropped, if this were a mouse or an elephant, have exactly the same acceleration. Gravity accelerates all objects at the same number, that number. Gravity pulls with different forces, and we'll get to that when we get to Newton's laws and stuff like that, right? But the force on an elephant is bigger. The force on a mouse is smaller, but they both accelerate at the same rate, meaning that if we drop them from the same height, they'll be going the same speed when they hit the ground. And free fall acceleration is that number. Notice little g is a number. It's a symbol that means a number. It has no direction in it. It's just 9.8. We will assign direction to it. Down is usually which way? Positive or negative? Okay. So, all objects in free fall being defined as only gravity. So, let's see here. Okay, I got this binder. So this is my textbook. Textbooks are useful for some things, including physics demonstrations. All right. So I'm going to take my textbook, and I'm going to take this piece of paper. I'm going to drop them at the same time. And what did I just tell you? They both hit at the same time, right? Okay, you ready? 3, 2, 1. I broke physics. I get a Nobel Prize. No, what is happening? Was this free fall? No. Why was this not free fall? There was air. There was air friction. Free fall is gravity only. Was gravity acting on the book? Yes. Was gravity acting on the paper? Yes. But there was also the air in the room, right? So to solve this, we need to evacuate all the air out of this room. How good are you at holding your breath? It takes about 56 minutes to evacuate all the air in this room, so just hold your breath that long. I'll turn on the vacuum pump. But I can make these hit the ground at the same time by being clever. Okay, you ready? It's a magic trick. You want to watch quickly because sleight of hand and all that kind of stuff, right? Okay, these will hit, they will fall at exactly the same rate and hit the ground at just about the same time. Are you ready? What did I do? I didn't get rid of the air, but I made sure that the air was affecting both of them the same, right? In effect, I made the air resistance a non-factor, right? The only thing then being left was gravity, and so they fell, right? The paper just kind of went with it, didn't it? Okay? And it did no tricks, no glue, right? Okay? So, in the absence of being able to suck all the air out of the room, right, we can do that. So why am I talking about this? Well, we want to be able to do problems just like we did horizontally, but up and down. And so I don't have time to do this whole problem, but we can set it up. And how are we going to set it up? Yeah, but how we're going to do exactly what we've been doing the entire lecture. Because it's vertical, has anything changed? No. Okay? It's just going up and down instead of sideways. But our process is the same. We're going to make a list, right? There's going to be, oh, not delta x, because x is reserved, isn't it? Delta y, okay, it's just a symbol switch. That's all it is. We're not moving the universe or doing anything weird here, okay? Well, we're doing weird things. So this isn't about the balloon, it's about the bowling ball, okay? So what's the initial speed of the bowling ball when it gets like let go of? Yeah, it was going up and then it's going to come back down, right? So it was, and I just managed to put that right in the way of my list. This is my cleverness on display. So we know initially it's going up positive 4.3 meters per second. What's its acceleration going to be? Once the pilot lets go? Which way? Down, right? Because it's in free fall. Do we know how long it takes to get to the ground? No, but in part A, that's what they're asking us to find, right? And then what do we know about its vertical displacement? Its displacement is not 56 meters. Negative 56 meters. Why is the displacement negative 56 meters? Which way did it go? Down. So it has to be negative 56 meters. We don't know how fast it's going when it strikes the ground. It's not zero. It will eventually come to a stop, but that's chapter 7 and 8. Okay? Right now, we can only do the free fall portion while gravity's acting. When it hits the ground, is gravity acting on it? Yes, but other things are too, right? The ground and other forces, right? So what does that suggest as far as solving this one? What equation might we want to use if we know delta y, a, v naught, but not v? Second equation, solve it for t, would be quadratic. You could also use third and then first if you want to avoid a quadratic. There's two different ways to do this. Often multiple ways to solve a problem. I'm out of time. I'll probably finish this one next time and then do chapter 3. We're going to do all chapter 3 next time we're together. But you've got enough here. It's critical that you think and ponder about the negative on that 56. Because that's the negative sign that's going to screw you up over and over again. Always check the direction that things are going. I'll see you tomorrow for lab. Have a great rest of the day.